So, today's lecture will be delivered by Dr. Kiran Hiremath. So, I hand over this session to Dr. Kiran.
Hello, good evening all. So ask, is slide window visible?
Yes, Kiranji, it's visible.
Right.
Okay.
Okay. All right. Right then. My name is Kiran Hiremath, and I'm with the Department of Mathematics at IIT Jodhpur. And today evening, we will discuss a few things about linear transformations. Yeah? Uh, Many of you are teachers, so you are already familiar with the broad content of this course. So my idea is really not to teach you content wise new, but to show you some of the connections that we need to highlight to students so that they feel connected with this subject and our delivery is more effective. So my main emphasis is on enriching the teaching rather than giving you anything new. So I want to keep this session more interactive. So please feel free to uh, discuss, interrupt, or ask query. I will be glad to answer your queries. Okay. So I suppose those among of us who are here, some may be teachers for engineering students, some may be teachers for science students. So, how many among you are actually teaching engineering students? Can you type it in the chat window? How many of you are teaching to engineering students and so I just want to ask you whether your teaching of linear algebra will be same for engineering students as well as science students. Feel free to switch on your mic and give your thoughts. So we are around 18 participants. Okay.
Sir, I think it is little bit different in between engineering students and science students.
Yes. Yeah. So do you experience this difference? What is the difference from your point of view?
Sir, I think for engineering students, it's very limited. It's introduction of vector space and introduction of linear transformation.
Yeah. Yeah. Okay. When
Student,
we
yeah.
when we look at mathematics, there are broadly two thought processes are involved. One is analysis. In the literal meaning of analysis is that to take things apart and take a close look. The second thing is synthesis. In synthesis, we put things together and make out something meaningful. So, when we are dealing with students of engineering or science, we have to deal with both the aspect of analysis and synthesis. We need to tell them that how to take a concept, divide it into sub concepts, take a closer critical individual concepts under. So this is one way of analysis. Then, once you have understood bits and pieces in great detail, start the process of synthesis. Okay? And in both the process involve asking questions. And asking right kind of questions are very important. And you will see that many times while teaching mathematics, we don't highlight this aspect that you ask some question and wonder what will be the answer, and that is the next step in the analysis. Or you just want to see that if we put together these two concepts, what is the interesting concept that we get. So one will take us towards applications, and second will take us towards understanding the working structure. So in today's discussion, I want to use linear transformation as a tool to show you that how can we create more interest among students while we are teaching this subject, and rather than just following the style of definition, theorem, proofs, and application, how we can challenge their minds, ask help them to ask critical question, and in turn see the linkages between the different concepts. So what's the plan for today? In the last week you have already seen the detailed discussions on vector spaces by Rana sir, and he also he basically defined what are vector spaces, gave examples, and then defined functions on the vector spaces. Just to recap, uh, the journey starts with a simple set is basically a collection of elements, and there is nothing interesting in that. We define two operations on this set. Yeah. So what are these two operations? Can someone pitch in? What are the two operations that we define on a set which will lead to
Factor
the notion?
addition and
Yeah.
scalar multiplication.
Yeah. And we have to keep in mind that these are not uniquely defined operations for a given set. Given set can have a different algebraic structure, that is this definition of vector space and vector addition and scalar multiplication. So even though the underlying set is same with a different underlying field or the defined operations of vector addition and scalar multiplication, we get different vector space structures. So this structure is more of a static kind of things. Nothing is happening. The happening starts when we start defining functions on these vector spaces. So that is what we are going to discuss in today's session. That if we want to define functions on vector space, how are we going to do it? So there are two ways of looking at this defining from the point of view of analysis. You see the underlying set, that is vector space, and ask yourself what kind of interesting functions we can define on them. And this is a there is a wide choice for that. We need to make appropriate choices, and some of the choices are meaningful, and some of the choices are challenging, and we see that we make a choice which is more meaningful for a given context. The reason why understanding this concept is important, and we should introduce it to the students in the context of linear algebra, is that here things are still very close to R or Rn. Students are well versed with R, R2, R3, R4, or Rn. So essentially, what we are doing in a vector space is that we are generalizing the notion that we are doing it in Rn. And this is the first step in the journey towards abstraction. Uh, from the vector spaces, we introduce the notion of norm, we get norm spaces. We introduce the notion of inner products, we get inner product spaces. Once we start defining, when once we introduce the concept of completeness, introduce the concept of convergence, then we can define additional notions like Banach spaces, Hilbert spaces. So this is really the fertile breeding ground where we are telling student that how things are done in mathematics or in a mathematical framework. So here is the broad picture. You have two vector spaces V and W, and let T be some function defined from V to W. And the broad notion of function is that function is basically a well-defined rule which takes element of V and then maps it to a specific element in a vector space W. We say V as its domain and W as its range. So let us define this concept precisely as we go further. So essentially what it's doing, it is taking elements of V and mapping to some elements in W. And in order to make sense, we have to make sure that one element in V is mapped to only one element in W. So this is the point where we should ask student that do we have any flexibilities here? Is it possible that one element of V can map to two different elements in W? And what is the answer? Answer is yes. It is possible to define, it's possible to map one element of V to more than one elements in W. But what is the difficulty in that case? Who can tell me?
It cannot be a function.
It cannot be a function. So how to motivate student to see that it cannot be a function?
One
Sir, it is not well defined. Yeah.
have two images. One element cannot
Okay.
have two images.
Yeah, but this we have to convince student that it can have two images, but then it's a problematic setting. How can we convince student? You see that I'm asking question and indirectly giving invitation to introduce some additional concept, mathematical concept. So what will happen if one element is mapped to more than one element in W? We miss something. What is that we are missing? We are going from V to W, but in some cases we also want to come from W to V, right? And
Yes.
as yeah, as Sandeep has pointed out, there is a problem with the inverse. Yeah, so when we define inverse, two different elements are getting mapped to the same element, and then it is disturbing the structure. So what do you think? What kind of structure is more natural in sciences? One-to-one mapping or one-to-many mapping? Obviously one-to-one. Yeah. So we think that one-to-many is not a good choice, right?
Yes.
Yeah. Okay. Let me give you hint. Suppose we are talking about analytic functions of complex analytic theory. Then you know that at some point we were told that we cannot define logarithm of a negative number. But in advanced complex analysis, we define logarithm of a negative number. But what is the price we have to pay there? Function becomes multi-valued. So functions can become multi-valued, but then we cannot do calculus on those cases. And in order to define some operations properly, we need to make a choice. So multi-valuedness is natural, but we have to make a choice. So by discussing this concept, I have also given the broad view to the students that inverse function is also important, and somehow we need to make sure that we can move between one space to other space smoothly. And this has a nice application when we probably in one of the coming sessions, when you study solving differential equations by using some of the techniques of linear algebra, you will see that this is very important, that you change the coordinates. You go from space v to space w. In space w, things are very nice. You perform some operations there, you get the answer, and then you find the inverse transformation and come to space v, where you find the original solution. So this concept is very important. That is the reason that we want this mapping should be one-to-one. So what is the situation here? We take element v1 and v2 of vector space v. If v1 and v2 belongs to v, their linear combination v1 plus v2 also belongs to v. Yeah, this is the basic property of vector space. Now let us say w1 is the image of v1 under the action of t, and w2 is the image of v2 under the action t, and this mapping is well defined. Then what can we say about if we have given this information, what can we say? Who can tell me? If this is the information given, t of v1 is w1, t of v2 is w2, then what are the various interesting possibilities are there? Please, I want to keep this session interactive.
T of V1 plus V2 equal to T of U1 plus T of U2.
Okay, is it right? Who is this speaking? Jay Kumar?
Yes, sir.
Yeah. So what is the opinion of other colleagues? Jai Kumar is saying that T of V1 plus V2 is equal to T of V1 plus T of V2. I will say that no, we cannot
No,
say
yes.
so.
If T will satisfy this linearity condition, then it is true.
Yeah, and I'm not saying so far that T is linear. I'm just defining T is some mapping.
In general, it is not true.
Yeah. So if we have this piece of information, T of V1 is equal to W1, T of V2 is equal to W2, W1 and W2 are elements of vector space W, then what is something that we can deduce? You know, in one of the stories of Sherlock Holmes, you know the detective story of Sherlock Holmes. Watson is amazed by Sherlock Holmes' ability to deduce so much information by mere observation, and he asks him that how can you do that? Then Holmes asks him, uh, Watson, you have been coming to my place so many times. Say yes. Uh, and you take stairs. Yes. Then he asks, do you know how many stairs are there? And Watson says, no, I have not counted. And then Holmes says that now this is the difference, that you see the stairs but you don't observe them. Yeah, information is there, you are seeing at it but you are not observing it. Observing it means you are also looking at underlying logical structure. So if I tell you that W1 and
We can see
W2 are elements of vector space W, what is the logical implication of this?
that W1 plus W2 is also.
In
So
V,
T
yeah?
of V1 plus.
Yeah. This is the most natural thing to expect. And now comes the interesting thing. Okay, I'm adding V1 and V2 in V. I'm adding W1 and W2 in W. But there is no connection between these two operations. And I want to define a function which basically sets the relationship between these two things. I want some logical structure should be there which connects the combination operation in V with linear combination operation in W. So our specific interest is in those functions between vector spaces which preserve the additive structure of linear combination. Lots of choices to define these functions, but we are making a very special choice. A choice of studying those functions which preserve this additive structure. Yeah. So what that means, now let us put a specific interest in mathematical term. So T of V is nothing but T of V1 plus V2, right? And I want to study those functions such that for which T of V1 plus V2 is T of V1 plus T of V2. Okay, that is also possible, but I want it should be W. So here basically what is happening that I am putting all the strings together, tying proper knot and saying that I want to look this pattern. Yeah. So what is our expectation that image of a linear combination in domain is linear combination of images in the range. Let's read the statement for a moment and then see what the above mathematical statement is saying. That image of linear combinations in domain is equal to the linear combination of images in the range. Am I right?
Yes, sir.
The mathematical statement is algebraic notion, whereas its interpretation is geometrical, right? And we are trying to play this interplay between algebraic understanding with geometrical intuition. Both are very important. Neither one of it is better than the other. Okay. So here I want to set the stage that what kind of function I want to define. So it doesn't make sense just to jump to the conclusion, say that linear function is defined as blah, 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 blah. Yeah. Why? Why only that definition makes sense? Yeah. So we have to give them motivation that why we want to do this. Yeah. Uh, one can have very specific interest, and many times these interests are coming from studying these kind of structures in variety of applications. And in many applications, we see these kind of things. For example, say if I turn the knob of amplifier by 1 unit, volume is increasing by factor 2. Turn it 2 times, then the volume is increasing by factor 4. So naturally, if I want to increase volume by factor 8, I know precisely how many times I want to change the knob. So linearity is very important. So what it is saying that T of V1 plus V2 is equal to T of V1 plus T of V2. And these kind of functions are called as linear transformations or linear maps. So we have to give first the broad picture and then introduce them to the formal definition that V and W be vector spaces, and mapping T V to W is called linear transformation if and only if it satisfies the property that T of U plus alpha V is equal to T of U plus alpha times T of V, where U and V are elements of V and alpha belongs to underlying set F. Now, if you look at this definition, there is something very important which is not explicitly mentioned in the definition. If we start putting all the minute details in the definition, or even the smallest of small detail in the definition, sometimes it becomes very bulky. So please look at this definition. Can you tell me what is the important thing that I'm not mentioning here and assuming it?
So both V and W are vector spaces over the same field left.
Excellent, excellent. That is what. Yeah. So we have to ask such kind of questions to student to make them sensitive that vector space is not just about the set of elements and then defining these operations. The underlying field also makes very important contribution. Yeah? Recall the example that we solved in last TEW session. Set of complex number is a vector space of dimension 1 or 2. What is the answer? 1, 2, both, I don't mind. What is the correct option?
If
With
it's over
respect to
R,
field,
then answer is 2. And if it's
Mhm.
over C, answer is 1.
Yeah. So it can be 1 or 2 depending on what is the underlying scalar field that you are considering. Yeah. So we have to highlight these kind of things. Then only students will see that, okay, underlying this set of scalars, scalar field is also important because eventually that will affect the dimensions. And this is very important, that how compactly we can store the information. And then some specific terminology. When the vector space V is same as vector space W, then we call it as linear operators. And linear operators are also very important. And then we collect all the linear maps from V to W. Let us denote this set as L of VW. Okay. So now for student, this statement looks very trivial. Okay, you just collect all the elements. Now, given this statement, what is the interesting question that you can ask? So if I give you this statement that collect all the linear maps from V to W, and let's denote this set as L of VW.
So till now this is a set. So which algebraic structure this set has?
Exactly. Yeah. You see that this is how we started our journey about vector space. We have a lifeless set, and by defining operations, we introduce some spice into it, and then we are going on the higher level. Now, the same kind of thing we are trying to do with these linear maps. You can also ask deeper questions. Yeah. For example, if I collect this set, yeah. So, what are the relevant questions that I need to ask about this set? Please tell me. If I have this structure, this set, one thing is that can we introduce some algebraic structure to make it a vector space? What are the other questions that we can ask? Yeah, Sandeep is asking, if V is equal to W, do we have to use this notion LVV? No, then it's not required. One can simply say LV. See, asking these questions will highlight some of the uncleared aspects in the understanding. For example, this how big is this set LVW? If it is a vector space, what can we say about the underlying field? Excellent question from Ushaji. So, what is the if we want to define vector space, if we want to make a vector space out of this, what are the choices available for us to define the field? Or I will ask even the rhetoric question. Do we really have a choice to choose field here if I'm considering LVW?
No, sir. I think the same underlying field on which V and W are vector spaces.
Yeah, actually we don't have choice. We have to stick with the same field which is there. Okay, coming back to this question. How big is this set? How big is this space? Set of linear maps from V to W. The first question. Is this question meaningful? How large, how big is this set?
Yes, sir.
This is a meaningful question. Yeah. So how can we quantify this thing? What is that notion available to us to quantify the largeness of a vector space?
This is
Basis,
Dimension.
dimension. Yeah, a single number, that is dimension. So by looking at the dimension, we can say that how large is this set. And why this number is very important, because later on we can actually study the embedding of one space into other space, yes, subspace structure. This is very important. Yeah. So the relevant question one can ask here, what is the dimension of this space? And if you see in all this definition, we are not explicitly defining V and W should be a finite dimensional space. Right now, these are just the vector spaces, maybe of finite dimension or maybe of infinite dimension. And uh, you all know that one of the standard question based on this LVW is that what is the dimension of LVW, right?
Yes,
If
sir.
if V is of dimension n and W is of dimension m, what is the dimension of LVW?
Mn,
Mn.
yeah.
Yeah. Yeah, so we all know these things, but we have to give motivation that why we want to know. It means that if we know mn functions which are mapping space V to space W, then we essentially know this structure. And what is the use of this information? Where do we use this information? Okay, we'll keep this question pending. So let's come to this set. Uh, now, in order to fix the ideas, now let us discuss some examples of this. So one of the classic examples is matrices. Let A be a m cross n matrix and define the mapping T from Rn to Rm. Uh, is isomorphic to, yes, yeah, right, yeah. So I'm seeing many of the answers are coming, which is very good sign that you are saying that what kind of underlying connections are there. Very good. So let us define the mapping T acting on X as AX. And the action we need to ask is that is T linear transformation? Answer is very obvious. Yes, T is a linear transformation, right? Am I right?
Yes, sir.
Yeah, yeah. So far this is very straightforward thing. Corresponding to this thing, we have to spice up this statement. This is how do we verify that T is a linear transformation? Who can tell me?
So we have to check T of x1 plus alpha x2 is equals to Tx1 plus alpha time of Tx2, where
Yeah.
x1, x2 belongs to this Rn.
Yeah. So basically, we are using the uh, basic definition here, right?
Yes, sir.
Yeah. So later on, we will study. So this is the point where we have to use some interesting thing that on a finite dimensional space, every linear mapping has a matrix representation. Right. This is one of the very cornerstone results of study of finite dimensional vector spaces. That every linear operator on a finite dimensional vector space has a matrix representation. So is the converse of this statement true?
Yes.
So every matrix represents a linear transformation.
Yes, sir.
Yeah. So this is the point where we need to force them to think in the other way. So in all these cases, what we are doing is that we ask some question, we answer it, and from that answer, we are asking further questions, which are deciding how things will evolve in the next course of action. Let us look at the next example. Define a mapping from space P3 to P2. P3, P2 are polynomials. P3 is a set of all polynomials of degree less than 3. Am I right?
Less than equals to 3.
Less than or equal to. Yeah. What is the reason that we need to consider less than? Why not just equal to?
So then it's not a vector space.
Then it is not a vector space. Yeah. So this very important concept that we need to remind to students that uh, the same set can be a vector space or not a vector space depending on slight change in the definition. Yeah. So we have to say that less than or equal to. And let us define the mapping as T acting on element P is nothing but derivative of P with respect to X. Is this T linear transformation? Okay. Can we
Yes.
use the same approach that we used to address the first question to answer this question? That is the basic definition of linearity.
Yes, sir.
Yeah. Any other way of answering this question?
Property of derivatives.
We can also use properties of derivative, right? So when we introduce the properties of derivative, recall 11, 12 standard mathematics. Did we use the word that derivative is a linear transformation?
Not
Did we
linear
use the word?
transformation there. We use the property of differentiation
Yeah. Yeah.
here.
So what is important is that we are already dealing with this linear transformation, but the only thing is that we are not looking at them from the point of view of linear transformation. And suddenly here from the analysis, we are taking the view of synthesis. It means that I have studied lots of operations which shows this kind of property. And actually, all these operations are the concrete manifestation of abstract concept of linear mapping, linear transformation. Yeah. So if you take the viewpoint of linear transformation, then taking derivative, integration, the operation may be different, but their mathematical structure, as far as action of an operation on the element is concerned, it's the same linear transformation, nothing new. And then we can derive lots of information from that. So it is very important that we need to highlight this both analysis and synthesis aspect of mathematics to student. So without using the definition of linearity, by using the properties of derivative, we can show that this mapping is linear. Okay. So am I going to, now I'm going to discuss the third example. Any guess what kind of example it will be?
Integration of a function.
Okay. What are other options? Any guess what is the next example I'm going to discuss?
Zero map, identity map.
Okay. How many participants are there? 23, and I'm hearing only 4 to 5 voices, very active voices. What about others? Ranjit ji, are you there?
Yes, sir, I'm here.
Yeah. So please tell me, can you guess what is the next example I'm going to study? It's
It is difficult to guess.
Sir, some linear transformation from Rn to Rn or something.
Or any vector
you see that
space
now
that
the
is in
pattern is
matrices.
building up. Some setting, a mapping is defined, and a question is asked. Is this mapping, is this transformation a linear transformation? And the way of solving this question is also more or less standard. Use the basic definition or some properties. Yeah. But this is where we need to introduce, if you want to reinforce some concept, sometimes you have to take the opposite viewpoint. So we have to enrich the instruction. So let us take this view. Define T from R to R2, where mapping is given by this. So is this a linear transformation? What is the answer?
Yes, sir. Rotation map.
Yes, very good. So it's also important to have geometrical interpretation. Is this a linear transformation?
Yes, sir.
How do we verify if it is a linear transformation?
It's a rotation by an angle theta.
Yeah. Anti-clockwise rotation by an angle theta. So can we use the same approach that we used to address first and second question to check if it is a linear transformation? That is
T of
T of
T of 0.
T of theta 1 plus alpha times theta 2, is it equal to T of theta 1 plus alpha times T of theta 2?
No, sir. Sir, we can use some simple property from the geometry of school level classes.
For example,
For example, multiply an angle by some constant. Okay, then we can if we have a vectors, so till this moment we haven't introduced the vector.
We can take even zero angle and then see that if T of 0 is 0 or not.
uh, 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 don't discuss this point. I will come to it. This is a very good observation, but let us not discuss that. Let's keep it aside for time being. So from the first two example, I set the expectation that some setting is given, operation is defined, and then you use the basic definition to verify if it is a linear transformation or not. So, and here I'm asking the question, is T of theta 1 plus alpha times theta 2 is equal to T of theta 1 plus alpha times T of theta 2? True or false? How to verify?
It is not true.
Take a paper and pencil. Replace theta by theta 1 plus alpha times theta 2. Use the expansion formulas for cos and sine, and then try to rearrange it, right? That's how one will do it, right? And what do we get? Why there is so silence? ऐसे ही करेंगे ना, या कोई और तरीका है?
We may take counter example.
Yeah, this is a counter example. But am I right? This is the way to verify it. Debashish is saying that it's not linear. Debashish, can you tell me how you will verify it, if it is a linear or not?
Sir, cos theta 1 plus theta 2 is not equals to cos theta 1 plus cos theta 2.
Yeah.
So this will not.
Essentially you are using the basic definition and then properties of trigonometric functions.
Yes.
Yeah. So so here is the example that not all transformations are linear transformations. Yeah. In fact, we are calling it as a rotation transformation. So it cannot be linear. Yeah, linear means it is going in a specific line, and here it's a rotation. So there is another important learning objective of introducing this example. Yeah. So basic definition of checking linearity is fine, but every time if we start using those definition, for example, just imagine, just for the sake of argument, I'm saying instead of cos and sine, I'm using Bessel function of first kind and Bessel function of second kind. Now, unless you don't know the properties of those function, it's very difficult to see that whether we can use the basic definition or not. So that demands that we need to probe further and see what are the special properties of these linear transformations. So that brings us to study of further study of linear transformation. And one of the simple, very nice property of linear transformation is that if V and W are vector spaces and T is a linear transformation, then T of 0 is equal to 0. Now, before we discuss this concept, I want to make you understand that this 0 as an argument of T is different than the 0 which is coming out. Yeah. T of 0, this 0 is 0 in vector space V and is equal to 0. On the right hand side is 0 in vector space W. So some authors will write that 0 subscript V, 0 subscript W. But when there is no confusion, we simply write it 0. But we need to interpret it in the context that this is 0 in that vector space. And we have seen in a tutorial example that this 0 need not be actual numerical 0. It can be also 1, 2, or any other number. I hope you recall that tutorial example.
Yes, sir.
Yeah. So this is very important characterization of linear transformation, that they map 0 in the domain to the 0 in range. So let us prove this. Okay, how to prove this? All I know is that vector space
Alpha minus alpha.
and
Some alpha in V and minus alpha in V, if we and try to use property.
yeah, we can go one step further and simply start with this very basic tautology kind of thing. T acting of 0 means T acting on 0 plus 0. 0 is the additive identity. So if I add to any element, I will get the same element. It may be that element itself. Okay. What is the next step?
Linearity of T.
Yes, T.
Yes. Yeah. This should immediately pop up in the mind. Use the linearity, then cancel T0 on both sides, which gives you T of 0 is equal to
0.
0. Yeah. And now look at this example from this proposition point of view. So who told this approach? Who was that?
To cancel, it is not a numerical, sir.
I was saying that T of 0 will not 0.
Yeah. Yes. Yeah. So what we have to do is that we have to see where the 0 is getting mapped. So in this case, what is the image of 0 in R? What is
It
the
will
image
be
of 0?
XY. Like,
It will be XY. Yeah.
this will be identity matrix.
Yeah. Yeah. So this shows that it can't be a linear transformation. So now the life is much simple. But before we go further, again, come back to this proposition and ask the question. T of 0 is equal to 0. Is it a necessary condition or it's a sufficient condition? Or both?
It's just a necessary condition. I
Okay.
can take the parabolic thing T of x is x square. That will be not linear, no?
Yes.
But T of 0 will be 0.
Yes. Yes. Yeah. So when we ask this question, it is basically exciting us to relate this concept that something we already know, and which will help us to get a better idea that this is the necessary condition. Yeah, but this is not sufficient. So it means that if I want to disprove, I can use this. But if I want to prove, can I use this? No. If it is 0 at 0, then I cannot say that I cannot conclude that it's a linear transformation. I don't know what it is doing to other elements. And the classic example is T of x is equal to x squared. Right. So let us come back to this new structure that we generated from the given piece of information. What is given? We have given vector spaces V and W over same field F. And without loss of generality, if I'm not mentioning underlying field, I always mean that it's the same field. And then we collect all the linear transformations on this vector space. And then just like we asked the question for the set, that when a set is a vector space, we can also ask question here that can we make this LVW as a vector space? And how to answer this question? If I want to answer this question, what are the things I need to do?
So first of all, we have to check the two operations.
Yeah. Is that all?
Like if T1 is a linear transformation, T2 is, then T1 plus T2 first of all should be a linear transformation.
Yes, that is the first operation, the addition of any two linear transformation we have to check.
Yeah.
And then the scalar multiplication when we multiply a scalar with a linear transformation. So
Hmm.
it will again a linear transformation.
Hmm.
And then the rest of the operations.
Rest of the like properties, like if zero is
Yeah.
there, additive inverse is there.
Yeah. See this, we need to ensure the existence of additive inverse, because additive inverse plays very crucial role in all this case.
Yes.
So definitely, the first important thing we need to define is this vector addition and scalar multiplication operation, and we need to also define what is the additive identity here. So we define, let us say, T1 plus T2 is defined as it's nothing but T1 plus T2 in the range. And since range is a vector space, this is a well-defined operation. We don't have to make any extra effort to give meaning to this operation. In case of scalar multiplication also, what we do, alpha times T is defined as alpha times T acting on V is defined as alpha acting on T of V. And since W is a vector space, alpha times T of V is meaningful as far as this scalar alpha is coming from the underlying field. Yeah. So in that sense, both of these operations are meaningful. And then the important question comes, what about the additive identity? What can be additive identity here?
Zero map, zero linear transformation.
Zero. And what it is doing?
Sending every vector to zero there.
Sending every vector
Vector E
in
to
V to
zero vector in W.
W. Yes. Yeah. So that is this. It takes all the vectors, it takes any vector V in vector space V, and it maps to zero vector in W. And with this, it can be verified that this is indeed and then here, to enrich the experience, we can ask the question that in all these discussions, we have not used the notion of dimension of a vector space. If V and W are finite dimensional vector spaces, what can you say about dimension of this vector space? So, so this gives a challenge that, okay, so what can be the answer? Whether this is a finite dimensional vector space, a vector space or not. If it is a finite dimensional vector space, what is the nature of basis element of this vector space? So we have defined vector addition, scalar multiplication, but what about the regular multiplication or product of two transformation? Can we define that?
We can
Can
use
we
composition.
define multiplication?
We
Yes,
can define
directly.
composition of any two maps.
Yes, yes. If the ranges and domains are properly defined, then we can actually define the composition. Yeah. And we can show that this composition is associative, distributive, and you see, if you look all these operations, it seems it's almost going in the direction of
Ring.
uh, ring. Yeah. So it
Yes.
just like a numbers, we can add them, we can multiply them, we can multiply one number by other number. Everything is happening. Yeah. So this is what is the algebraic structure we are talking. Yeah. So this is the this is what is at the heart of linear algebra. We want to explore this. So it is, I mean, when you look at this vector space, it is reminding us a lot of familiar properties of numbers that we know. So naturally, a question comes whether all the properties which are satisfied by real numbers or a complex number are satisfied by elements of this vector. What is a guess? So again, this is the question of analysis.
The properties of a real number being a ring must be satisfied over here, but property being a field, that may or may not be.
Okay, any specific case you are referring to? So this is the invitation to look at thing that we know in a critical point of view. That is what is analysis. Analysis is not seeing at the thing, but observing it. What is some operation that we do with the numbers and we simply don't bother to give respect to it? It doesn't matter. It's the same thing. You do this way or you do that way, the same answer. I'm giving you hint indirectly. Come on, come on. I have already given you the hint.
Commutative
Say
property.
it again.
Commutative property.
Can you be more specific? You are on the right track.
Is A into B is same as B into A in the numbers, but same thing is not true in function.
Yes. This multiplication of maps is not commutative. Yeah. S composite T need not be same as T composite S. Yeah. So in that sense, these numbers are very special. Yeah. We can get some many properties of those numbers in this space, but not all properties. And then here is a very nice question. So suppose if this is true that S composite T is equal to T composite S for any T and S in this element, then what happens? Yeah, and this is very, very important. Uh, Linear algebra has lot of applications in quantum mechanics. Yeah, quantum mechanics has two kind of formulations. One by using Schrodinger equation, which is very difficult to understand for physicists because it requires some.
Then in quantum
Yeah,
mechanics, we have this simultaneous diagonalization thing, which we
yeah.
like when
There is a
operators
there
commute.
is a yeah. Uh, we are referring to the version of quantum mechanics which is called as a matrix version of quantum mechanics, where operations are basically the result of measurements defined. And for example, first you measure the velocity, and then you measure the first you measure the momentum, and then you measure the position, or you do the other way. Will you get the same result or not? So this commutativity is very important property, and when the operators fail to satisfy this property, there is some important implication of it. So we have to bring this thing in the context of application, that if something holds true, where it will lead. If something fails to hold true, where it will lead. Right. So if time permits, we will come to further aspects of this vector space of linear transformation from V to W. Let us come to these other things that you already know. Some of the important sets associated with linear transformations. What are these sets? Range of T and null space of T, right? We all know definitions of this range of T. Range of T is nothing but you collect all the images of elements of V that defines the range of T. Range of T is a subset of W. Now, help me. which version of saying this is right? Range of T is a subset of W, or range of T is a subspace of W?
So it's a subspace.
Okay, now I have not verified it, right?
Most probably this subset.
Yeah. So, but when we are introducing this definition, if you focus only on this definition, if only this definition is given, then what
It's
is,
the only subset.
yeah, if only this definition is given and nothing is proved, I have to say range set. But of course, we'll go further and we'll say that this set is in fact a subspace. Same case with the null set of T. The other name for it is that kernel. So it is set of all elements of V which are mapped to 0 in W. So these are the some of the important sets associated with the linear transformation. So this is the place where for the first time we introduce the finite dimensionality of these vector spaces. Yeah. If V is a finite dimensional, then we define the dimensions of this range of T and null space of T. The range of T is called as rank of T, and dimension of null space of T is called as nullity of T. And from here, we go one step further and ask the question, are these just sets, or they also have some algebraic structure with them? And answer to that question is yes, they are not just the sets, but they also inherit the algebraic structure of their mother's space. That is, in case of null space, it inherits the algebraic structure of V, and R of T, that is range of T, inherits the algebraic structure of W. So I want to use these two examples to see that how we can use proof as a demonstration of synthesis. So it means that we know the individual facts and we need to combine these individual facts to come up to a deeper observation which is not immediately available. Yeah, look at this range of T, null set of T, these definitions, these are just looking at the things but not observing it. But when you observe it, you will say that these are not sets but these are subspaces. Let's think about null space of T. So the first natural question we need to ask that, are we talking about some meaningful sets or not? Is this set empty or non-empty? So what is your take? Is null space empty or non-empty?
Non-empty, zero exists.
Non-empty.
Zero is there? How can you say so?
T is a linear map.
Say it again.
T is a linear map, so T
Yes.
of 0 is 0.
Yes. Yeah. We know that at the heart of linear transformation that it maps zero element to zero element. Yeah. I'm talking vaguely, but it means zero element in a domain to zero element in range. That's what I want to say. So it is definitely non-empty. So it makes sense to talk about. Then what is the next thing we need to prove if we want to show that this is a subspace? What is the subspace verification criteria? Do we have to verify all the properties of vector space?
No, sir.
No. Then what are those minimum properties that I need to verify?
It is closed under addition and scalar multiplication.
Addition
Yeah.
and scalar multiplication.
But this is not enough. What else we need to do? 0 also belongs to that set, right? Do you agree with me? Is it required to show that 0 also belongs to that space?
Yes, yes, sir. Otherwise, it will not be a vector space.
Yeah. So we need to verify two things. The first thing, whether the 0 element belongs to that set or not. And the second thing is the set closed under scalar multiplication and vector addition defined on the mother subspace, mother space. That will give the proof of this. So I'm quite sure that you already know how to prove this. But what is important too is that these two statements are opportunity to synthesize the pieces of information that we know. Yeah, we know the individual facts, but we need to combine them. In the same way, what are the things we need to check if we want to show that range of T is a subspace of W? Take any two elements in range. If they belongs to range means what? What is the inference you can draw from this statement? W1 and W2 belongs to range of T. Means what?
W1 and W2 are images of some vectors in the domain.
Yes. There exist vectors V1 and V2 such that their images are W1 and W2. Okay. Then if I take linear combination of W1 and W2 in W, the question is the vector in the domain whose image is this linear combination? That is the linear combination of, we need to verify that this linear combination W1 and W2, does it also belongs to range of T?
Yes, sir.
And
There will be the linearity of T.
yeah. So in this case, we transfer all the operations on V. Yeah, we do the operations on V and then see what is happening in range of T, and then we can prove this. And this thing gives us the another important theorem, nullity theorem. Yeah. So what this is the theorem of speciality of finite dimensional vector space, which is saying that if V and W are finite dimensional vector spaces, T is the linear transformation between them, then rank of T plus nullity of T is equal to dimension of V. Or if we define in terms of the spaces, it means dimension of range of T plus dimension of null space of T is equal to dimension of V. Okay. So I know that you all know the proof of these things. Do you carry out this proof when you teach linear algebra in your classes? Can you share with me what kind of difficulties students face, or you find it challenging when you prove this theorem to students? Remember, this is teachers enrichment workshop. I know that you know the proof of this, no doubt about it. But my question is about what kind of challenges students face, or what kind of challenges you face to prove these things to students, or convince these ideas to students.
Take example, they can understand easily.
Yeah, definitely. To appreciate abstract thing, it requires a training of mind. But for concrete thing, because we can touch them either physically or with the hand of mind, then it is easy to do it. But seeing it something with the eyes of a mind is very difficult, but it's very powerful. And you know that maths is also called as science which makes invisible thing visible, of course, in mind. What kind of challenges student face when we prove this? It's again like that. They know all the essential ingredients. It's just like mixing those ingredients in a proper way and argue with them. And if you want to enrich the teaching learning experiences, we need to bring forward those underlying things so that they can appreciate that all the facts that we have learned in analysis. When we do analysis, we are taking things away from its application and looking it in isolation. It's like a surgeon operating on a patient in ICU, where everything is extremely high. But once the patient gets well, he goes the outside world. He is experiencing lots of perturbations, but still his body accepts, works, and opposes those perturbations. The same kind of thing here.
How to visualize
So let me show you that. Yeah,
how to visualize these concepts. The students cannot relate to it so easily, as you said that it is very abstract. So the picture, they
yeah,
cannot take the picture inside their mind when we are teaching.
yeah, yeah. And they need to also learn some, as they called as tricks of trades. So what are these tricks of trades? The first thing is that divide the problem into simpler problem. Solve those simpler problem, and then go to the next level of the problem. Yeah. And what is important is that when solving problem is a kind of art, you need to assume something so that things will be streamlined. So let me demonstrate this broad idea with the proof of this theorem. I know that you know the proof. My purpose is not to give the proof of this statement to you, but to tell you that how to prove this, how to entice or direct the minds of students so that they will go towards proof. Yeah. So one way of proving thing is that you eliminate all those illogical consequences, and then what remains is the logical one, and that will prove the thing. But for that, we need to do the proper setup. Okay, so let's look at the. So what is the setup? It's not a part of given statement, but we have to start the constructions that. It's given that V is a finite dimensional vector space. Let's call let n be the dimension of this vector space, and now define the null space and the range space of T, which is involved in this theorem. So null space is set of all elements of V which are mapped to 0 under the action of T, and range is basically collection of all the images of elements of V. Now, look at the statement, dimension of V that I'm assuming n. So let me also assume dimension of null space of T, that is K. So if I tell that null space of T is K dimensional, what is the conclusion of this? Or what can I construct from this? If null space of T is equal to K means what?
There are k elements, there are k vectors which reaches to 0 in the group.
Yeah, this is the next thing that should come to the mind. So it means that there are k elements v1, v2, vk in V such that these k elements are the basis of V. Okay. So what is the second conclusion of this choice? Look at the vector space V. Part of this vector space V is null space. Null space is of dimension k. And I know that the vector space is of dimension n. What that means? It's sheer play of logic. Can I extend this basis, yeah. So Sindhu is saying that it means that n minus k have a zero image. What is the other way of saying? It means that there are another n minus k vectors, vk plus 1, vk plus 2 till vn in V, such that if I consider this v1, v2 till vk and add them this additional element, they form the basis of V. Now, is this statement clear? This is very important, that given a linearly independent set of dimension less than the dimension of a vector space, it can be extended to the basis of a vector space. So do you agree with me? Why this should be possible? I don't agree. It's not possible to have add some more elements to it to make it the basis of V. Can I say so? How can we prove this statement?
If they are linearly independent.
Yeah. But here the thing is that there exists another n minus k vectors.
But we don't know right now whether they are linearly independent or not.
No. This statement is saying that there exists another n minus k vectors in V such that these new n minus k vectors with these earlier k vectors, they form the basis of V. So it means they are linearly independent.
Linearly, okay.
This is just because
Again, this is referring to one of the questions of the tutorial that show that every finite dimensional vector space has a basis. Right? So if it has a basis and it is of finite dimension, it means there must exist n linearly independent vectors. If I know k out of that, I can search rest of n minus k and make it complete. How to do that? Well, it can be a daunting task, no doubt. But at the level of logical reasoning, it's possible to do that. So let us remain there and then accept this. Yeah. So this proof,
For doing
yes,
that, we can the T map, like we have this vector and then we will have the null space. So we can even go to the quotient vector space to see our remaining basis of V.
yeah. But you see that that requires the introducing the concept of quotient space and then defining operations on that, uh, which
Yes,
uh, which can be left for the later stage, but not at this level.
yes.
Yeah. But this is a good point to say that okay, there is a alternative way of doing this. So, Dilpreet ji, till what time? How much time I have?
You have around 5 minutes.
5 minutes. Okay. I think I may still 5 more minutes
Okay.
so that I can conclude it. So please
Okay.
bear with me.
No problem. Okay.
So to prove this theorem, essentially what we have to show is that rank of T, that is the dimension of range space of T, is n minus k. So that means I need to somehow get hold of n minus k vectors, which can act as a basis for range of T. And I don't have to look here and there. I can take this set and apply T on that. So what is happening if I apply T on these elements v1, v2 till vn? What is happening to first k elements?
They're gonna be 0.
They are going to be mapped to 0. Yeah. So then let us look at remaining elements, T of vk plus 1, T of vk plus 2 till T of vn. And then we'll show that they will act as a basis of R of T. So that's the whole argument. So to show that something is a basis, we need to prove two things. One is the span is equal to the entire space, and then this set is linearly independent. Right? This is what these are the two things we need to show. So let's first show that the span is equal to entire space. So what is the meaning of span is equal to entire space? It means that if I take any element of range
Like
of T, it should belong to span. And if I take any element in the span of this set, it should be in R of T. That's what we want to do it. So let us take element V in a vector space V, and I can represent this vector in terms of the basis of V. Now, help me. What is the next thing I'm going to do now? There are not many options here.
Take a
right,
transformation
yeah.
on the side.
Yeah. Let us look at image of this, because you see, my ultimate question is with the range of T. So I have to go to the range space. So that's what I will do. So I know that T of V belongs to range of T. And what is this T of V? I apply T on this basis representation. And then it's a familiar game. Since T is a linear map, I can take it inside summation. I can take this constant outside. Yeah. Now this is the summation from 1 to n. But do you have to consider these n terms, or can I simplify it?
Yes, we can take the last n minus k because all
Yes.
other T of pi is 0.
Yeah. All of them will be mapped to 0. So we have to consider only from k to n. And this thing belongs to range of T. Now you see that what I'm saying, that if I start with T of V in range of T, I'm getting its representation in terms of all these n minus k elements. And if I start with this and add 0, I can go back and I will see that it belongs to range of t. So what essentially we are saying that every vector in range space can be expressed as linear combination of these vectors. So we can say very well that span of these vectors is equal to range of t. But to qualify as a basis, we need to also show that they are linearly independent. So again, we fall back to the basic definition. If you want to show that they are linearly independent, we consider the linear combination from I running from k plus 1 to n. Excuse me, here is typo here. It should be k plus 1, right?
Yes.
First k elements are mapped to 0, so it should be k plus 1. Yeah. So take the linear combination of this n minus k element. And we need to show that the only solution of this linear combination is a trivial solution. This is what is the basic definition. So we are playing with basic definition here. So in this case, the game is going in the reverse way. So we start with this, take constant inside, take action, take the summation inside. Yeah. And then all these things is equal to 0. Now, what I know is that all this V1, V2 till Vk and Vk plus 1 to Vn, they are the basis of vector space V. So it means that they are linearly independent. And here I'm considering only part of it. But I cannot say that only part of it is linearly independent. From this, I cannot conclude it. So what I do is that let us look at this t acting on this summation ci vi I from k plus 1 to n. Let's call this as v tilde. So where is this v tilde in vector space V? When t acts on this linear combination, it is giving me 0. So where is this? Yes, as Arun says, this must be in null space. There is no other way. And I already know that null space has k basis elements. So we can express this v tilde in terms of k basis of null space. Now I have two representation for v tilde. One is in terms of its basis element and other that I'm obtaining from my assumption. So from here, we can say that this difference must be equal to 0. So let us write it in a compact form. Summation alpha I vi, I from 1 to n is equal to 0. Alpha 1 to alpha k are my di's, and then alpha k plus 1 till alpha n are my minus of ci's. So are you with me here? I'm just rewriting it here. And this summation alpha I vi is a vector in V, and this summation of this is equal to 0. So if this is equal to 0 means what? All vi's are the basis of vector space V. By definition of linear combination, what it means?
All alpha i's are 0.
There is no other way. All alpha i's must be identically equal to 0. It means all these di's must be equal to 0. So that implies that this T of Vi are linearly independent. They span the range of T. It means they are basis of range of T. And how many of these elements are there? These are n minus 1k. And that proves the rank nullity theorem. So this theorem is a good exercise to train the mind that how to go for deductive logic and how to go for synthesis logic, where we are putting things together and trying to construct it. In one part it is deductive, and in the other part it is synthesis, and this is what we need to train the mind. So please keep in mind that many of these students will find it interesting if you tell them that if you take it as a logical challenge, then this is basically it's a mind game, that how we are putting things together to deduce something, or from the given thing how we are extracting the important piece of information. So some of the things of this linear operator and the corresponding matrix representation that I discuss in tomorrow's session on eigenvalues and eigenproblem. Okay, so thank you all. Let me stop here. If you have any queries or questions, please feel free to ask me on my email address. I will type my email address here. And I wish that your students will enjoy doing mathematics. Thank you all.
Thank you very much, Kiran.
Thank you, Dilpreet.
Thank you for this was a wonderful talk, and
My pleasure.
we chat that people enjoyed this talk. Thank you very much. Okay, so everyone, and tomorrow we will meet at 5:30 again to continue this discussion. Okay, thank you. Bye.